Swayam Prabha. Digital India. Educated India.
Welcome to the next session on Pharmaceutical Organic Chemistry Paper 3. In the Unit 1, we are studying about stereoisomerism Part 1. In the last lecture, the lecture 4, we will be studying about racemic modification and resolution. I am Dr. Balaji, currently working as Associate Professor in the School of Biotechnology at Jawaharlal Nehru University. This project is sponsored by DTH Swayam Prabha, MHRD, New Delhi. In this particular session, we will be studying about racemic modification. So what is racemic modification? And we will also be studying about resolution of racemic mixtures. So from the racemic modification, can we isolate individual enantiomers or not? That we will be studying in this particular session. And how are the different types of resolution of racemic mixture also we will be studying in this particular session. We will also be studying about asymmetric synthesis and total and partial synthesis. The difference between total and partial synthesis. Let us now study about racemic modification and resolution. So in the previous session we studied about the last one, which is the racemic modification. Especially what we have seen is in a chiral starting material, and when we don't use any chiral reagent, the product obtained is always a racemic modification, because we always end up with 1:1 ratio of both the isomers or the enantiomers. So in this particular session we will be studying about the next step of that. That means how can we separate this racemic modification to give or get the one of the enantiomer. So this process is basically called as resolution. So we already know a mixture of equal amount of enantiomers are called racemic modification and is generally denoted by plus or minus symbol. So that means the optical activity of that particular compound or molecule is basically 0. And since the enantiomers have every physical properties same, like they have same boiling point, melting point, and density, and every physical property is same, due to which we cannot apply any of the separation techniques which are generally used, like the physical separation techniques like fractional distillation, fractional crystallization, and achiral chromatography, because of course we can isolate the enantiomers in some HPLC conditions. Both the isomers can be resolved by forming the diastereomer. So other than those cases, we cannot even isolate enantiomers by normal column chromatography. So here what we study is basically the separation of enantiomers. That is the mixture of enantiomers into constituent enantiomer, that is R and S mixture is separated to get R isomer and S isomer. So this kind of separation is called as resolution. So in other words, separation of enantiomers are called as resolution. In fact, we studied this particular case long back, like Louis Pasteur was first the person to isolate both the enantiomers by this particular resolution method. So what we did was the obtained sodium ammonium tartrate was optically inactive. So using the microscope, he identified there were two types of crystals, and he painstakingly isolated the left-handed crystals and the right-handed crystals separately, and then he took the optical rotation of this one of the isomer, that is the left-handed enantiomer and the right-handed enantiomer separately, and he found out that these two compounds were basically optically active. But when these two are mixed in 1:1 proportion, the net result was optical inactivity. So from that, he first identified and resolved the isomers using physical separation. So that is the only exceptional case in the entire organic chemistry that this sodium ammonium tartrate was the first and the most important one, which can be separated easily by crystallography or crystallization. But later on, many people tried many other compounds, but they could not be resolved by this simple crystallization techniques. So even now, this is considered as the most promising and the very first example of resolution of enantiomers by simple crystallization method. There are other methods we will be looking at one by one in this particular session. So let us look at why the enantiomers cannot be separated, because they have every physical property same. So we cannot easily separate them out. But how we can separate them is by converting them into different type of compounds. So when an enantiomer, that is 1:1 mixture of HA and HA plus and minus, is reacted with a base, that is basically in this particular case we are talking about HA is an acid and base is nothing but an alkaloid. This alkaloid is optically active alkaloid. So that is the reason we are taking one particular isomer. And this isomer now forms salt with both the acids, the plus acid and the minus acid together. So we have the H acid and the minus base, that means minus base plus acid. So this is one product, and the next one is minus base and minus acid. These form another base. So we have two different products are formed in this particular reaction. So they are called diastereomers. So since these are diastereomers, they have different physical and chemical properties. So they can be easily separated. So that is how an enantiomer is converted to a diastereomer, and the diastereomer can be separated by column chromatography or fractional crystallization or fractional distillation methods. And once they are separated, the separated thing can be regenerated. The enantiomer can be regenerated by treatment with, in this particular case, since we have added a base, we add an acid, then this gives back the enantiomer. One of the plus enantiomer is isolated separately, and treatment of this one gives the minus enantiomer separately. So in other words, the plus and minus enantiomers, which were non-separable in the beginning, were converted to diastereomer, and the diastereomers were separated to two different compounds, and two different compounds were treated with acid separately to give both the enantiomers separately. So a racemic modification can be converted to separable diastereomer by treatment with an optically active reagent. So this is what is called resolution of enantiomers. Now we have some examples given here. An acid, if the starting material is an acid, it can be reacted with an optically active base like brucine, quinine, like optically active bases can be used, and treatment of that acid base reaction leads to diastereomer formation, and the diastereomers can be separated, and from that the pure enantiomers can be regenerated. And if it is a base which we have to resolve, what we can use it? We can use tartaric acid, mandelic acid, and Mosher acid, like various acids are there. They can be treated with bases, and they will form the diastereomer that can be separated, and the pure base can be regenerated. And if we have to separate alcohols, we can convert them into esters by treatment with an optically active acid chlorides, or we can also convert them into urethanes with isocyanates, optically active isocyanates. If we have to separate aldehydes and ketones, we can use hydrozones which are chiral. With that, we can actually separate the enantiomers. And if it is amines, we can convert them into aneles by treatment with the chiral aldehydes. And if it is amino acid, we can convert them into acyl derivatives with acid chlorides. So by these starting materials can be converted to various diastereomers by treatment with an optically active reagent. So this is what is called resolution of enantiomers. In this chart, we will be looking at various ways by which enantiomerically pure compounds can be synthesized. One is based on asymmetric synthesis. In the asymmetric synthesis, we have fermentation method, chiral building block method, chiral auxiliaries, asymmetric catalysis. So we will be in this particular session studying more about these kind of asymmetric synthesis methods. And there are some non-selective synthesis methods, and the resolution of racemics are also known, which is called kinetic resolution. We will be looking at both the enzymatic and the chemical method in this particular session. There are also other methods called liquid-liquid extraction, membrane separation, separation through diastereomer formation, crystallization, and chromatography. So these are basically, many of the things are physical methods, so we will not be looking at in this particular session. And there is also another type called the chiral pool synthesis. So the chiral pool is basically some of the starting materials from which an enantiomerically pure compound can be synthesized. We will also be looking at some of the examples in this particular session. These chiral pool compounds are generally obtained from plant or animal source. That is, they are basically naturally obtained compounds. Let us look at some of the methods in detail now. So the first one is the chiral resolution. So in the chiral resolution, we can actually use multiple methods. One is the crystallization reaction. That is, tartaric acid, mandelic acid, quinine, etc. can be used as derivatizing agent or resolving agent. So if we have a base, we can treat the base with the tartaric acid or mandelic acid. That will form diastereomer salt. Once the diastereomer salt is formed, they can be separated, and then from that the pure enantiomer can be regenerated. Now, other method is the enzymatic resolution method. In this reaction, in this particular resolution method, what we do is basically, this is based on the different reaction rate of enantiomers in the presence of enzymes. So we already know enzymes are stereospecific reagents for many reactions. So the reactions catalyzed by enzymes are always stereospecific. That means only one of the isomer is formed in 100%. So by using that method, we can actually separate some of the enantiomers by forming some derivatives. The next one is the kinetic resolution. This is based on the different reaction rates of the enantiomers. So in the enzymatic resolution, basically enzymes are responsible for the differential reaction rates, whereas in the normal kinetic resolution, it is basically based on the reagents which are employed for the reaction rate difference. So the first one is the chiral resolution. So here we will be looking at the crystallization method. So as we mentioned earlier, the tartaric acid or mandelic acid, quinine, or 1-phenyl ethanamine, these are all the different reagents which can be used. These are some of the examples, not the complete list of examples. So any of these compounds can be used for resolving. So here we are using basically the 1-phenyl ethanamine as the resolving agent. So we have two, the enantiomeric carboxylic acids are there. So these two carboxylic acid, when treated with an amine, forms the salt. So these two compounds are basically diastereomeric salt. So they have, what is a diastereomer? Diastereomer will have the configuration of one carbon same and any other carbons are different. So that is the reason in this particular case, if you have the chiral center, this and this are having the same configuration, whereas these two are having opposite configuration. So these two are basically diastereomeric salts, and since these are diastereomeric salts, they will have different physical properties. Since they have different physical properties, we can use crystallization method or column chromatography or many other method to separate them. In this particular case, we are using crystallization. The different rate of crystallization of these two salts can be employed to separate these two diastereomers. Once these two diastereomers are separated, then what we can do is we can cleave this particular amine part from this carboxylic acid by the treatment of an acid that regenerates this particular enantiomer in single 100% pure form. The same way this acid also can be separated. So in other words, these two enantiomers can easily be separated by crystallization methods. The next one is the enzymatic resolution. So in this particular case, we already know this is based on the presence of the enzyme, the reaction rates are different. And this is generally used for the resolution of natural and unnatural amino acids. So we have a unnatural amino acid shown here. This is having a trifluoromethyl group, and we have a amine and carboxylic acid. So this is the alpha amino acid. This is treated with acetic anhydride to form the N-acetyl derivative. So once this N-acetyl derivative is formed, this is subjected to hydrolysis by acylase. That means the acyl group is cleaved by this particular enzyme. This cleaves only one of the isomer exclusively. So the other isomer is not at all hydrolyzed. That is the reason, because this actually involves the catalytic site, and in the catalytic site only one isomer, one of the isomer can fit very nicely. The other isomer cannot fit. So we will be studying about that in the coming few lectures. So this particular isomer which actually fit in that enzyme pocket is hydrolyzed very easily, and we end up with 100% of one isomer. So this racemic mixture is now converted to the chiral isomer. But in this particular case, we are actually getting only 50% of our product. It is not a 100% conversion, because in this particular case, we have 1:1 mixture of both the isomers. But we could isolate only one isomer in the product. The other isomer is again recycled back. So the next method is the kinetic resolution. So in the enzymatic one, we use that in the presence of enzymes. In the case of kinetic resolution, we generally use some catalyst. So in this particular case, the phenylethanol is treated with the catalyst in the presence of acetic anhydride and the base triethylamine, gives this corresponding acetate derivative. So the catalyst structure is shown here. So this is the chiral reagent which is employed for this kinetic resolution. So there are some conditions which are required for this to be successful. One, the inexpensive racemate and the catalyst should be used. Then only these kinetic resolution methods are commercially possible. And it should be easy to separate the starting material and the product. In this particular case, we have a alcohol and we have a acetate. So this is a ester, this is an alcohol. So these esters are basically less polar compared to alcohol, so a column chromatography can easily separate them very easily. So that means these are possible to separate the starting material and the product. And in these cases, the resolution basically proceeds at low catalyst loading. This is very, very essential, because if we have to use a large amount of the catalyst, then kinetic resolution is not a successful method. And when no other method is possible, then only people generally go for kinetic resolution, because this is not a very pronounced method for separation. Then the next one is the chiral pool synthesis. As we mentioned earlier, chiral pool synthesis basically depends on the natural sources. So the starting materials are generally derived from natural sources. In this particular case, we are using diethyl tartrate. So this is mainly used for carbohydrates and amino acid separation. So the D-mannose is basically the carbohydrate. Okay, this is the starting material. And this starting material is commercially available in large quantities from plant sources. And this can be converted with multiple steps to the swanesonine. So the bicyclic nitrogen derivative is shown here. This compound can be synthesized starting from D-mannose. So this is one example of chiral pool synthesis. In this particular case, a naturally occurring, naturally available carbohydrate is used as the starting material. So the next one is the chiral auxiliary. So what is a chiral auxiliary? This is basically a chiral compound that is temporarily incorporated into the molecule like a handle, and then that handle is removed after the separation is done. So this moiety basically controls the stereochemical outcome of that particular synthesis. Say for example, this schematic representation gives a rough idea of how the whole process works. So we have a prochiral reactant. So this is the compound which is our starting material, which we actually want to resolve, and this is converted to some derivative by treatment with the chiral auxiliary. So this is the chiral auxiliary part is added to the molecule, and then we are introducing a group in this particular compound with the help of this chiral auxiliary. So this specifically prevents attack from one side, and from another side only the reaction actually proceeds. So that is the role of this chiral auxiliary, which prevents the reactions from taking place from the other side. It is not 100% efficient, but of course in many cases it is very good. And after the reaction is over, this chiral auxiliary is broken down and the functional group, original functional group is regenerated. So from a prochiral reactant, that is the starting material, we ended up with the chiral product. So here this is the center where the chirality was introduced. So these kind of things are possible using chiral auxiliary. Let us look at some of the examples. So in this chiral auxiliary method, so here we have a starting material. This is 1, 2, 3. This is a propanone derivative. So this compound is actually converted to the chiral product by this particular reaction. So in this particular case, this unit is our chiral auxiliary, and this chiral auxiliary is introduced on this particular carboxylic acid by the amide bond formation reaction. And then we carry out these kind of reactions. The benzaldehyde is added to this carbon in a very specific way. So as we mentioned here, this is how the reaction actually proceeds in a highly stereoselective manner. And what the product we get is basically the syn product, because the reaction occurs in this carbon, which is alpha to the carboxylic acid. So this is the carboxylic acid which was converted to the amide using the chiral auxiliary. So this is the carbon where the reaction actually proceeds. So this is the place where the benzaldehyde unit is attached. So this is how, after the reaction is over, this amide unit is broken down by the lithium hydroxide. That is a mild basic hydrolysis leads to the removal of this particular group, and then we end up with the syn product. So this is how the chiral auxiliaries are employed in organic synthesis. The next one is a chiral reagent. So in this particular case, we will be looking at stoichiometric reagent. That means we are not talking about the catalyst, we are talking about the reagent. So here a chiral reagent basically induces stereoselectivity to an achiral substrates in a chemical reaction. So we have already seen earlier, an achiral system cannot give chiral product if no chiral induction or chiral reagents are used in that reaction. So continuing the same, if we say If we have to get a chiral product, somehow there should be a group or a reagent which induces chirality into the molecule, and these are all the reagents which can be used for inducing chirality. So here we have given one example, binol is shown here. So this is the chiral compound, this is the chiral center, and the same there is another compound that is a diisopynacamphenyl borane is shown here. This is the borane unit. We have the two chiral units which are present on this borane. So this is used as a chiral reagent, and this is used for borane reactions, hydroboration reactions, and in that particular case we end up with a chiral product. Basically, hydroxy derivatives are prepared using hydroboration reaction. And binol is used for reduction of carbonyl groups mainly. There are other reactions also which are used using these stoichiometric reagents. The next one is a chiral metal catalyst. So the metals are basically used in very small quantity or a catalytic quantity, because in the previous one we had seen stoichiometric quantities of reagents, but metals are generally used in catalytic quantities. So the Sharpless epoxidation reaction as shown here is one such example. So the dihydroxylation, this is a dihydroxylation reaction. So in this reaction, osmium tetroxide is basically used, so that gives basically the dihydroxylated product. So here we actually get this DHQD, and fall is the mixture of the reagent that is employed in this particular reaction. So this mixture is called AD, asymmetric dihydroxylation mixture. Beta is the reagent that is used in this particular reaction. So it has both the thalazine unit, that is the PHAl, and dihydroquinidine, that is the DHQD2. So these two form a complex in the presence of the osmium metal to give the required dihydroxylated product. Along with that, there are other metal catalysts that can be used, include titanium, platinum, palladium, rhodium, iridium, copper, etc. There are plenty of metal, especially many transition metals are used as the chiral metal catalyst in many reactions. Rather than metals, the next one is the organic compound itself is used as a catalyst. Basically, it is a form of this organic catalyst is a form of a catalysis in which the rate of a chemical reaction is increased by the organic catalyst. And basically, in most of the cases, proline is the catalyst which is used in many of the reaction. So this starting material can be converted to Hajas-Parrish ketone using the chiral catalyst with just 3% of L-proline. So this is also another example of organocatalysis. So these are all the various ways by which an asymmetric synthesis can be carried out. Let us look at some of the advantage, disadvantage, and the examples of the methods whatever we had seen so far. The first one is the resolution. Here the advantage is both the enantiomers are possible, because using resolution method we can get both the isomers. This is cheap, and many times this is scalable. Industrially we can scale this reaction. But the major disadvantage is we actually lose 50% of the other isomer when we do the resolution. Only one of the isomer is obtained, so the maximum yield is only 50%. And say for example, if we have to do crystallization, we have to do multiple times, and after 3 or 4 cycles the efficiency goes down drastically. Some of the examples which are used is L-tartaric acid, S plus mandelic acid are some of the reagents which can be employed in this resolution method. And in the case of enzymatic resolution, here we don't have to use any chiral auxiliary, and many times enzymes are cheap, so this is a better method. But the limitations are This requires optimization quite a lot because enzymes are generally sensitive to many reaction conditions, so they have very limited scope. Some examples are given here: lipase, acylase, etc. are some of the examples of the enzymes which can be used for enzymatic resolution. And the next one is the chiral pool synthesis. It is a very good method because the starting materials are naturally occurring and they are plenty, so they are very cheap, and moreover the reaction produces 100% enantiomeric product. So this is a very good method for the preparation, but it is only possible because we generally get only one of the enantiomers. Both the enantiomers are not naturally occurring. And another major drawback is, even though we get 100% enantiomeric excess, the reactions requires multiple steps and the overall yields are going to be very low. So these are some of the disadvantages of using chiral pool. Some examples include amino acids and sugar derived compounds are the basic starting materials for many asymmetric reactions. Then the chiral auxiliary is basically, it gives excellent enantiomeric excess, and these reactions are also highly selective. So this is a very good method, but again the major drawback is to introduce the chiral auxiliary and to remove it we have to do 2 extra steps. In other words, the reaction overall yield decreases, and moreover if we have to generate a new chiral auxiliary, that also requires multiple steps to synthesize. So this is also sometimes very expensive to make. Even though we get very good excellent enantiomeric excess, making that chiral auxiliary and then increasing 2 number of steps are all some of the disadvantages. Some of the example is the Evans oxazolidinone, which we had seen in our reaction, that acid was converted to an amide cyclic one, that is oxazolidone is the one which is formed. The next one is the chiral reagent. So basically this gives high EE and these are highly selective, but optimization is very essential in this particular case, and only very few reagents are successful, and they work only for few substrates, not for every substrate. And binol boron reducing agents are some of the examples. And in the case of chiral metal catalyst, so only a very small amount of recyclable material, that is the catalyst, is used. So it is a very economical method and it has a high industrial application. But some of the metals are very expensive, like rhodium, platinum are very expensive, and moreover it requires a lot of research and development to identify the right catalyst for that particular reaction. Examples include sharpless asymmetric epoxidation, dihydroxylation methods, etc. And the last one is the chiral organocatalyst. The major advantage of this one is, in the case of chiral metal catalyst, they are prone to undergo oxidation and they are sensitive to moisture. So these two are the major limitations of using chiral metal catalyst. But the organocatalysts are very good in that particular case. They are not sensitive to oxygen and moisture, and they are also very cheap, and they don't have much of the toxicity as seen in many of the metal catalysts. But the major disadvantage is it requires lots or extensive development, and it is very difficult to design. Most of the organocatalysts are basically proline based. So with that we have compared all the different asymmetric synthesis methods. Let us recap what we have seen. Some of the things, like if we have to talk about the chiral compounds, that is R and S, we say this is based on CAP rules, and when we say D plus isomer or L minus isomer, that is related to optical rotation, and D and L are basically the Fischer projection for sugars and other thing we have studied so far. Now let us look at total and partial synthesis. We can also call this as a total and partial asymmetric synthesis. So what is a total synthesis? Total synthesis is nothing but it is a complete chemical synthesis of a complex molecule, basically, or most importantly from a natural product, from a simple commercially available precursor. So if you are going to synthesize some naturally occurring compound from a simple starting material, that is what is called total synthesis. And if we get the right enantiomer or the right stereoisomer, then we call that is a total asymmetric synthesis. And this particular method generally should not involve or does not involve any biological process. Say for example, enzymatic resolution is one of the steps. In this particular total synthesis, we are not, or we generally do not use those kind of enzymatic reactions. The next one is the partial or semi-synthesis. This generally refers to a process involving the aid of biochemical process. So enzymatic reactions can come here, or synthesizing a known intermediate from which the final product can be made. So these are the difference between total and partial synthesis. Let us see, we are starting with a compound A, which is converted to compound B, which is then converted to compound C, which is further converted to D, which is the final compound we want to make. So if A to B to C to D is carried out completely, then this is called total synthesis. But on the other hand, if A to C is synthesized and we already know C to D is known, then we say A to C synthesis is basically a partial or a formal synthesis. The same way, instead of starting from A, which is a very cheap or a commercially available thing, instead of simple starting material, we are starting from some intermediate, and from this intermediate we are going to the final product. So these two are basically called as partial synthesis. Now we have given this compound is a ibuprofen compound. This is synthesized from isobutyl benzene following various reactions. So the first one is the Friedel-Crafts reaction, then we have a base catalyzed reaction, then we have a hydrolysis reaction, we have acetylation reaction. So we have then finally we have hydrolysis reaction also. So we have various reactions involved. This is nothing but the enzyme formation. So in all these reactions, 1, 2, 3, 4, 5, 6, 7. 7 compounds are involved. Starting from 1 to the final product, we have a lengthy synthesis procedure. So this is basically the Booch process, the company's synthesis of ibuprofen. So can we call this as a total synthesis? Now the major question is, what is a total synthesis? The total synthesis should get something, some compound that is naturally occurring, and it should also start from a simple starting material. So this synthesis, does it meet that criteria? I don't think so, because first of all, this is not a complex molecule. Second, this is also not a natural product. So when this is not a natural product, this is not a complex molecule, the synthesis, although it involves multiple steps, not be called as a total synthesis. So you need to now know the difference between normal synthesis and a total synthesis. So total synthesis always involves a complex natural product. Now let us look at the most promising compound for cancer treatment, which is Taxol. So we will now talk about what is asymmetric synthesis. Basically a chemical reaction or a reaction sequence in which one or more new elements of the chirality are formed in a substrate molecule and which produces stereoisomeric products in unequal amounts. So these are all the examples. In other words, in simple terms, what we say is you start with the compound A. The compound A gives two products, B and C, let us say. This B and C are both stereoisomers. B is formed in large excess compared to C. That's it. So you are making actually from A, you are making B and C, out of which B is one of the stereoisomer which is formed in large excess. That means you have a asymmetric synthesis of compound B. And if it is asymmetric total synthesis, our end product has to be a naturally occurring compound. So that is the only difference. Asymmetric synthesis means any single step can give one of the stereoisomers in large quantities. If it is a total asymmetric synthesis, the total means basically it is a complex molecule. And if you look at this compound, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 stereo centers are there. if we assume 2 to the power n stereoisomers are possible, so we are going to get 2 to the power 10 stereoisomers for this particular compound. So that means how complicated the synthesis is going to be. So that is why the asymmetric synthesis, that is the total asymmetric synthesis, is always a very great challenge. And when these kind of complex molecules are synthesized, they are published in very high quality journals. Now, let us look at what is the partial asymmetric synthesis. So, the previous compound, what I said, is the Taxol is formed by the total asymmetric synthesis. Casey Niccolo was the first person to report its synthesis, and this compound is the most famous one in his paper. The final compound Taxol can be prepared from this particular intermediate. So when we talk about partial asymmetric synthesis, we are not going to prepare the final compound, because from this intermediate the final Taxol synthesis is already known. So what people do is they synthesize this compound by a different or a new method and say we completed the partial asymmetric synthesis. So in this particular case, Nakada and their group had shown that this starting material can be converted to this particular intermediate using a palladium catalyzed reaction. So this reaction formed only one intermediate. So what they said was this is a partial asymmetric synthesis of the final product. This is not the total asymmetric synthesis. So this is how we differentiate. When we do the synthesis up to a certain intermediate, we call that as a partial synthesis. Here is another example where Sato and Chida group had synthesized this particular intermediate. So from this paclitaxel can be synthesized. That procedure is already known. So this starting material, that is the ABC ring, was converted to this particular final intermediate. So this again is called as a partial asymmetric synthesis. So this is how we can actually differentiate between what is a total synthesis, what is a total asymmetric synthesis, and what is a partial asymmetric synthesis. Let us look at Fischer interconversion, basically 90-degree rotation. Why 90-degree rotation gives the other stereoisomer, we will now look. So the compound given is shown here. The aldehyde group is at the top, the CH2OH is at the bottom, hydrogen and OH is on the pointing towards the observer. So for this compound we can assign DL notation, but of course we will go through the RS configuration so that it is much easier to understand. So according to Fischer notation, these two groups which are projecting towards the observer, the hydrogen and the hydroxyl groups are actually pointing towards the observer. So to give the RS nomenclature, we have to give the priority to these groups. So in that priority, we do need to know between CHO and CH2OH which group gets the highest priority, because the first connection atom is carbon here. Here also the first connection atom is carbon, and the next connection atom, if you look at, is one is hydrogen, other one is double bonded oxygen. And in this carbon, there are two hydrogens and one oxygen. So if you look at very carefully here, every double bond is actually converted into single bond. So that is the reason, if you look, one OH is there, that is one oxygen and two hydrogen. Here it is going to be two oxygen and one hydrogen. So this gets the priority compared to this alcohol. Primary alcohol gets the next priority, aldehyde gets the next highest priority. So oxygen is the highest priority group, so this is given number 1, and followed by the aldehyde is getting the priority number 2, and the CH2OH is getting the priority 3, and the hydrogen is the least one, which is getting the least priority. So if we have to assign a configuration, RS configuration for this compound, according to RS nomenclature, the hydrogen has to be away from the observer, but in this particular case the hydrogen is pointing towards the observer. So this is one thing you have to always remember. So if we look at the molecule, it is actually looking like this. Now let us go and watch the molecule in the 3 dimension. So this is the 3-dimensional representation of the molecule. Priority number 1 is given to the O. For clarity, I have removed the hydrogen atoms from the aldehyde, hydroxyl and the CH2OH groups, and I have only kept the hydrogen which is attached to the central carbon because we have to assign the priority. So the oxygen gets the highest priority number 1, followed by the aldehyde which gets number 2, CH2OH gets number 3, and fourth one is the hydrogen. So if we look at the molecule, this is actually pointing towards the observer. So this is the observer and it is actually pointing towards the observer. And for RS nomenclature, what we have to actually do is the hydrogen has to go, that is the least priority group has to go away from the observer. So I rotate the molecule very carefully in such a way that the hydrogen goes behind. So now if you look at the molecule, the hydrogen is away from the observer and the highest priority group 1 is here and 2 is here, 3 is here. So if you look at the clockwise or the counterclockwise direction, the priority group goes from 1, 2, 3. This is in the counterclockwise direction. So this is the S isomer. If I give the stereo assignment to this one directly, you can see the software can actually give the stereo assignment. So I just put the chirality here and say OK. So we assigned the chirality, and when we rotate the molecule, we will see the S configuration is given to this center because the hydrogen is away from the observer and the priority groups are in the counterclockwise direction. So the assigned configuration S is for this particular carbon. Let us come back to our 2D representation of the same molecule. So we had seen this is in the counterclockwise. Since the hydrogen is pointing towards the observer, whatever we get, we have to actually give the opposite configuration. So this, if you look at here, 1, 2, 3 are in the clockwise direction and hydrogen is pointing towards the observer. So we have to give the opposite. This is 1, 2, 3 clockwise is R, but hydrogen changes it to S. So that is what we had seen here. We have the S isomer here. Now if we do a 90-degree rotation, what happens? All the groups are getting converted. The CHO which is at the top comes to the right. The hydrogen goes to the bottom. The CH2OH group goes to the left and the OH group goes to the top. So this is how we did the 90-degree rotation. Now let us look at how to assign the RS configuration for this molecule. Now the hydrogen is away from the observer. The OH is also away from the observer. CHO and CH2OH are pointing towards the observer. So let us give the priority numbers as earlier. So OH is number 1, CHO is 2, CH2OH is 3, and hydrogen is 4. And if we look at the molecule in the 3-dimensional way, it is shown as here. Let us go to the 3-dimensional view for this molecule and see how it is actually represented. So this is the exact assignment. 1 is here, 2 on the right, 3 on the left, 4 at the bottom. So now here is the three-dimensional representation of the same molecule. OH is at the top, CHO is at the right side, CH2OH is on the left hand side, hydrogen is at the bottom. So for convenience, I have not shown the hydrogen for the hydroxyl group, aldehyde and CH2OH, because this becomes much easier for us to visualize the molecule. Since the hydrogen is away from the observer, what we can actually do is we can directly keep the molecule like this. And now let us assign the RS configuration. 1 is at the top, 2, 3. If you go from 1 to 3, it is in the clockwise direction. So this is actually R isomer. Let us find out how the software assigns the assignment. So chirality I put and say apply. So we have R configuration. So this is a much easier way to understand. When we do a 90-degree rotation, the S isomer actually become R isomer. In other words, whenever we do a 90-degree rotation for Fischer representation, this always leads to the opposite configuration. So let us come back here and see the two-dimensional representation. So we get whatever we are getting is a R isomer. So in effect, the first compound is having a S configuration at the chiral center. On 90-degree rotation, that leads to R isomer. In other words, whenever you are doing a 90-degree rotation, what you have to do is you have to actually assign the opposite configuration to the chiral center. So in an easy way to understand this is, if the hydrogen is actually projecting towards the observer, then the easiest method is just do a 90-degree rotation, and once you do a 90-degree rotation, the hydrogen goes away from the observer. If it is in the vertical axis, it has to be converted to the horizontal axis. So the horizontal axis, the group is away from the observer. So once you do that, and then you can easily assign the priority groups, and you can actually identify what is the actual configuration. So if it is an R isomer, then before the 90-degree rotation, the compound is going to be S isomer. So that way you can easily make or assign the RS configuration using for the Fischer projection compounds. In summary, let us recap what we have studied so far. We have studied about racemic modification. We also studied about the resolution of racemic mixtures. So two major types we have studied. One is the kinetic resolution, another one is the enzymatic resolution. We also studied about asymmetric synthesis, which include chiral pool as the starting material, chiral auxiliary, chiral reagent or catalyst. The catalyst can be either metal catalyst or an organo catalyst. So these are all the various reactions we have studied. And we also studied about what is the total synthesis, total asymmetric synthesis and partial asymmetric synthesis. With this, we conclude this session. Thank you.